Should I start calling all my lectures by that? It's lecture 1, lecture 5.1. All right. Design stage uncertainty analysis.
You're trying to be too suave there.
I can't help it. So,
Protect the flannel. I don't like this
It's
guy.
the jacket.
oh yeah, I love the V-neck. You know, I don't know what's up with crew necks. They try to choke me. V-necks are like they're there so you can maybe breathe. I believe.
The scale reading high.
Yeah. I have a your mama joke I'm not gonna say right now. So
Even with a PhD, you don't think about your mom.
I do all the time. I just can't say them anymore. At least not on YouTube. Okay. Design stage uncertainty analysis is the type of analysis done when designing a measurement system before actual measurements are made to predict the uncertainty in measurements made by the system being designed. So early on in the process, we're saying, we need to measure this. Maybe we could use this instrument. Maybe we could use this sensor. Let's try to figure out how much uncertainty we might have in our measurement. But we haven't built one yet. We haven't tried to prototype it. We don't really know for sure what our uncertainty is in the measurement. We haven't actually measured anything with this system. So we're trying to estimate what it would be. So we're trying to design a good system, but we haven't been able to build a prototype yet and take any measurements with it. Okay. So it comes from different sources in a measurement system, which will now be considered. So there are different aspects of the system that can contribute to our uncertainty. Often at this stage, we do not classify each uncertainty as systematic or random, although we probably could. It's usually kind of early on in the process, and we're going to be using really rough numbers, and so we don't get super precise with classifying the different types of error or uncertainty. So, a little word on the difference between error and uncertainty, because they get used interchangeably a lot. Error gives us uncertainty. And that's essentially, when somebody says the error of this instrument is like 1 millimeter, say it's measuring length, so 1 millimeter error, we essentially just say, oh, that's our uncertainty. Is whatever the error is, it's an error that we say, oh, we're uncertain to that amount of what the error is. So sometimes people will give it to you in a spec sheet as being an error, and you will take that to be an uncertainty. Sometimes they'll say this is an uncertainty, in which case you still take it as an uncertainty because, we're cautious like that.
So error is meaningless.
So it doesn't mean that. Error means that it's off from its true value, or that it can be off by this much, or this is a typical number for an estimate for the systematic error. So if no device is calibrated perfectly, you might say. So like if it's trying to measure a mass of 1 kilogram, every device is going to be systematically off to one side or the other, up or down. So what they do is they will give you, maybe they calibrate it, and their calibration gives them a 95% confidence that you'll be within 0.1 kilograms at 1 kilogram, and that's what they'll tell you. The error is 0.1 kilograms, and then you have to say, oh, that's my uncertainty, and if they don't give you a probability, you have to assume it's 95%, which we'll mention.
So if that's uncertainty, then we could say that we're then 95% certain. It seems like it's almost repetitive.
Yeah, it is a little. They're slightly different concepts. Error is typically
The numerical value of what you're off by.
Yeah, so it's maybe a property of a device. So like a device might have a certain error associated with it. It's just like a systematic error of 0.1 kilogram at 1 kilogram. That would be an error associated with a device. That gives us an uncertainty in our measurements. So when we use that device that has a certain error associated with it, that amount of error gives us uncertainty about it. We don't know what the actual error is of any given measurement. We just have to base it on probabilistic models, essentially. So I'll show you how to try to quantify that, although it is a little bit tricky. And so when we see error, we interpret that as, okay, this device has some error associated with it, but they're guaranteeing that it's within this bound. Okay, so they're gonna say we're confident. I mean, it might be better than that, but it's not going to be worse than that. So we can have a certain confidence that it will be within this range. And then when we describe the uncertainty, we say, oh, okay, well, we know within 0.1 kilograms what the weight of this is. That's our uncertainty. So we're uncertain. We're very confident that it's 1 kilogram plus or minus 0.1 kilograms, for instance. We have a 95% confidence or something like that. So yeah, there's a little bit, it's like subtle, it's just two sides of the same coin. The error is on the device side, the uncertainty is on our side as the person who's measuring something with the device. Okay, great. Zero order uncertainty, U0, is uncertainty due to instrumentation resolution, which is, so, I mean, the term arbitrarily is a little bit, a little harsh, but it's kind of accurate. It's considered to be U0 equals 1/2 times the analog resolution, which we say we have 95% confidence in, and this applies to analog measurements, or I should say to a resolution given in terms of an analog system. Then there's also what we would do if we have a digital readout. So some devices have like a digital readout, like a voltmeter. And what we take for the zero order uncertainty is one least significant digit. Yes.
Mm-hmm.
That was checked too. Okay, so just like that song, this does not stand for the drug. This is just purely engineering. Did you know that some of the first people who used LSD in the United States were engineers in Silicon Valley? What became Silicon Valley? It's a true story. Digital.
That makes more sense.
Yes. Thank you. So yeah, so if you're looking at a readout, a digital readout, and it's got, 3.26 volts, this is the least significant digit. So 0.01. Whoop, there's not an extra point there. 0.01 is the zero order uncertainty. And if you have a resolution, so in the manual, a lot of this comes down to being able to look it up in the manual, because that is primarily the source of how we estimate uncertainty in the design stage. There is a resolution associated with a device. Almost all devices, especially analog devices, will have a mention of resolution. If it doesn't have any mention, oftentimes we just ignore that in our uncertainty estimate, our design stage uncertainty estimate. Yeah. Some instruments have error estimates in their manuals. This is called instrument uncertainty UC. Occasionally this is given as a single value, but more often several contributing elemental errors are given, such as linearity error, which comes about due to nonlinearities, and hysteresis error due to a lack of symmetry in a measurement's increase versus its decrease. So I think you guys probably, did you guys talk about hysteresis in your like chemistry class or physics class? Well, we'll hopefully talk about it a little bit more at a later point, but hysteresis essentially is the lack of symmetry in how a device responds in one direction versus the other direction. It's quite annoying, but how it's typically mitigated, or not even, well, there are different ways of actually mitigating it when you design a measurement device, so you can try to get rid of it. But there's often some amount that's left over in certain types of devices. It's really hard to get rid of it. So they try to minimize it to a certain point, and then whatever's left over, they throw into this bag and call it hysteresis error. They say, yeah, we got it close, but like, you know, it's not perfect. Which is always true, right? We can't make devices behave perfectly. Just mitigate things to the point where their effect isn't too significant. And the hysteresis error, hopefully, isn't going to be something that makes your measurement crappy. And it could. All right, the root sum squares, or RSS method, allows us to estimate the total instrument uncertainty UC due to the elemental uncertainties UK, with the number of elements K, big K, as UC equals the square root of, so the big sum from little k equals 1 to big K of each of these elemental uncertainties squared. So the root sum square. The RSS method can be used to combine design state uncertainties of concatenated or series instruments for a measurement. I think this is a typo, and this was supposed to be design stage. Design stage uncertainties. Concatenated instruments for a measurement as well. So, for example, it's not just the uncertainties within a given device. So, you know, within the device you might have the linearity and then the hysteresis errors, and you can combine them using this formula. But you can also combine the design stage uncertainties for an entire device with another device if their measurements are taken in concatenation. So, for instance, a force measurement with a force to voltage transducer and a multimeter. That would be an example. So where you're taking a force in to the transducer, it outputs a voltage. So there's some uncertainty associated with that device. And then you have a multimeter that's measuring that voltage, which also has its own uncertainties. So you can estimate the propagation of that uncertainty by using this RSS method. Now, it's important to realize that so some measurements are made directly like this, like a voltage is made which came from a force, and we make that measurement. Other times, we measure one thing and we use it in a formula to compute something else. And so we can't use this method necessarily directly. We're going to have to learn how error propagates or uncertainty propagates when you start using formulas of different measurements, and we'll have a whole discussion of that specifically. But when you just are going from one device to the next device, measuring the output of that, you can just use this RSS method. Okay. Does this feel a little bit like we're just making up this root sum square method? Yeah, we are. We are. So there's a lot of... this is a really weird topic. So measurement gets really weird once you get down into the nuts and bolts. And we started talking about the theory that goes into it at the beginning of this. Well, building standards and the SI and the NIST and all of that stuff, that is actually quite interesting stuff. And this is a method that they recommend, and it really only is valid because it seems to work okay. I don't know of any theoretical derivation of why this works okay, but it does seem to work okay. It's not that bad. When we start out with this approximation, the later approximations that we can get by studying it more in depth show that it's not bad. So it's the best we can do without doing a whole lot of work. So that's kind of nice. Okay. The confidence/probability level, P%, depends on the confidence of each error estimate. Okay, so your zero order uncertainty, okay, your device uncertainty for each device along the way. These all have some confidence or probability level associated with them. Now, we're mostly looking these values up in the spec sheets, right? So if no confidence level or probability is given, which is really common, it is common to use 95% as the percent confidence in that value. It's best to at least, to try to at least be consistent. I mean, when you have devices that have different levels, you might have to adjust one number based on the normal distribution. If it's given at it's like 68% or a standard uncertainty, you might have to adjust it to a 95 based on the z-score table. It's best to keep them consistent. A lot of times nothing's given as a probability, so you use 95% for everything. And that is as ill-formed as it sounds. It really is. It's just it's not a part that I like of engineering. It makes me uncomfortable. It's not like there's no clear way to go about it. Everybody's just kind of like doing their best to estimate stuff. However, if you end up giving your boss one day a report that has design stage uncertainty and a 95% confidence in it, trust that it's like standard engineering practice that if you estimate it this way, that's a reasonable number to give. So if you hand your boss a report, first off, your boss will be impressed that you were able to do this because so much of engineering goes on without any discussion of confidence intervals or the uncertainty associated with a given number. Error bars. Oh, if you include those, boss impressed. Guaranteed. Okay. The design stage uncertainty for an instrument is defined as this. So you take the root sum square of the zero stage uncertainty based on the resolution of the device, and you combine it with the device uncertainty. So that is our design stage uncertainty value. I'll just finish it, and then we can do the example on Wednesday. This is an estimate of our uncertainty based solely on information about the instruments. This should be considered an estimate of our minimum uncertainty. Okay? Factors we will later consider will add uncertainty. So when we start to consider the random error aspect, especially when we start to take measurements and we have sample statistics from our actual devices, then we can get a better prediction of our uncertainty. Okay? So for now, we think of this as being like, this is an optimistic value. It's great for saying this would never work, or this could work plausibly. It's great to tell you at that stage whether or not this could possibly work, or not. I mean, it could be, and it really sucks if you go through and you design this whole measurement system, and you get to the end and you realize, oh, this was never going to work, right? Like there was no way this could work. If I had just done my design stage uncertainty analysis, I would have known that. But I can never get values that I'm confident enough in to matter. So for instance, like maybe you need to know what the weight of something is within a certain bound. If you do your design stage uncertainty and it tells you that to have a 95% confidence in it, your bound's like 4 times larger than the bound you need, it's probably not going to work that way. You're going to have to find different instruments, different sensors, what have you. So it's good to help you early on to decide, like, is this a good direction to go, bad direction to go, and then when you get down to it, your factor of your uncertainty might double or triple, or maybe go up by a factor of 0.2. It's hard to say, but at least your initial value led you to believe it could work. It's possible that it could work. And you propose something like, hey, boss, I want to spend $20,000 to prototype this in 2 months of my time. It helps if you have a little confidence level in there. Like, this is the confidence. And that would be the design stage uncertainty. So we're going to do one for this measurement, and I think it's pretty fun. We're going to use a microcontroller in here because I'm doing this problem. So I like microcontrollers. So yeah, we're going to do this on Wednesday.